Hi everyone, my name is Chehami Fadhila. I'm a third-year PhD student in physics from the University of Tizi Ouzou. I would like to present some of my results on the FDTD simulation of a conical silver nanocoupler based on C-shaped waveguides. I will first start with a brief introduction, then recall some of the theory behind the light guidance and confinement phenomena and in the FDTD framework. Then I will present the simulation results performed on a two-dimensional C-shaped waveguide and on our proposed three-dimensional nanocoupler constituted by a conical succession of C-shaped waveguides. I will end with a conclusion and some perspectives. The development of photonic integrated circuits has achieved great progress in terms of rapidity, compactness, and profitability. Studies show, however, that during the light transition from an optical fiber at micrometer level to an integrated waveguide at nanometer level, very high losses are generated because of the mismatch existing between the two devices. Therefore, many studies have developed transitional devices called couplers, which play the role of optical funnels destined to focus the light coming from a large to a small area with minimum optical losses. Our work consists of exploiting the fundamental mode of a C-shaped waveguide to design a nanocoupler able to ensure a highly subwavelength light focusing with good transmission and coupling coefficients. We define the waveguides as optical devices which are able of guiding the light in a given direction. Waveguides could be dielectric if they are constituted by dielectric materials only, or plasmonic if they are made of metal and dielectric. While the nanocoupler is defined as an optical device intended for confining the electromagnetic waves or splitting one input signal into two or several output signals. The nanocoupler could be used as an isolated device integrated on a chip with the waveguide or fabricated on the fiber. The coming simulation results have been carried out using the finite difference time domain method based on the spatio-temporal discretizations of the Maxwell's equations following the Yee scheme. Here we show the schematic representation of a C-shaped waveguide constructed from a classical cylindrical waveguide to which we add a metallic part controlled by the angle beta. Rho and Ri are respectively the inner and the outer radii of the classical cylindrical waveguide. First, we have to confirm the nature of the C-shaped waveguide fundamental mode. To do this, we inject a random signal near the structure in order to excite all the cavity frequencies. After that, we calculate the spectral energy density displayed over here, which exhibits a cutoff wavelength of the fundamental mode at lambda equal 1560 nanometers. Then we calculate the electric intensity distribution at the cutoff, which shows one lobe of energy, thus confirming the TE10 nature of the C-shaped waveguide fundamental mode. In this slide, we are going to display the variation of the fundamental mode cutoff in terms of the different geometrical parameters of the C-shaped waveguide. At the left side, we can see that by decreasing the outer radius, the cutoff exhibits a linear variation when the outer radius is far from the inner one, and a nonlinear variation when the outer radius becomes closer to the inner one, due to the coupling between the two plasmonic metallic interfaces modes. At the right side, we see that the cutoff shows a linear behavior in terms of the additional metallic part beta. Therefore, we exploited this sensitivity in order to optimize the different C-shaped waveguides constituting our nanocoupler. Now, we show the schematic representation of the designed nanocoupler constituted by a conical succession of four C-shaped waveguides previously optimized in order to ensure the most efficient coupling phenomena. In order to quantify the efficiency of the coupling phenomenon, we calculate the transmission spectra and the power flux incident near the base and transmitted near the end of the coupler. Here we show the spectral variation of the transmission and the power flux calculated in the case of four different couplers by varying the number of C-shaped waveguides constituting each coupler. When looking to these curves, we notice that by increasing the number of C-shaped waveguides, both the transmission and the power transmitted through the coupler decrease. This indicates that the most efficient nanocoupler inducing a subwavelength light focusing with a good transmission and coupling coefficients is the one containing three C-shaped waveguides. Besides, we can notice that the transmission spectra exhibits three peaks at lambda equal 1560 nanometer, lambda equal 1366 nanometer, and lambda equal 1042 nanometer. So, in order to explain their origin, we calculate the electric intensity distribution corresponding to each peak plotted in the next slide. On the one hand, we see that the horizontal electric intensity distributions corresponding to the three peaks exhibit one lobe of energy referring to the TE10 fundamental mode. On the other hand, we notice that the vertical electric intensity distributions show different behaviors. We can notice that the one corresponding to lambda equal 1560 nanometers shows an uniform illumination due to the constant phase during the back and the forth of the light propagation, which confirms the excitation of the fundamental TE10 mode. Meanwhile, at lambda equal 1366 nanometer and lambda equal 1042 nanometer, we can notice respectively 1 and 2 intensity nodes corresponding to the first and the second harmonic of the TE10 fundamental mode. So, until here, we can deduce that the cutoff wavelength of the fundamental TE10 mode of a C-shaped waveguide is very sensitive to the variation of its geometrical parameters. This sensitivity has been exploited in order to maximize the resulting coupling phenomena. The nanocoupler, constructed by a conical succession of three C-shaped waveguides, enables a high subwavelength light focusing with a good transmission and coupling coefficients reaching 70%. So, this kind of devices could be efficiently used in several optical applications such as optical trapping and sensing. As perspective, we consider to exploit the C-shaped waveguide to design another coupler configuration enabling the signal splitting. Thank you.